You are welcome to the PLBC program. My name is Dr. Aliuda Musa Mohammed. You are highly welcome to this platform. The lesson we are going to present this morning is metals and their compounds. Metals and their compounds. When you check in the periodic table, the elements that we have in the table, they are broadly classified into two. That is the main classification, either metals or non-metals. Their classification is based on their physical and chemical properties. So this morning we are going to discuss about metals and their compounds. Well, metals, they are defined as electropositive elements. When we say electropositivity, we are referring to the tendency of an atom or element to release an electron so that it will be positively charged. So metals are generally electropositive elements. They have this tendency to release electrons so that they will acquire positive charge. The number of electrons they release determines the number of charges they will have. For instance, if you have elements like sodium or lithium, which are in group 1, when they release one electron, they will acquire a single positive charge. And elements like calcium, magnesium, which are in group 2, when they release 2 electrons, they acquire 2 positive charges. Elements like iron 3 or aluminium, iron and aluminium, when they release 3 electrons, they acquire plus 3. This is an example. This is sodium. It releases 1 electron to become positively charged. And when you take magnesium element, by releasing 2 electrons, it acquires 2 plus. So electropositivity is the main criteria we determine whether an element is a metal or not. Metals are electropositive elements. And another thing that you need to know is this. When you look at the periodic table, which I believe you have in your books, in your textbooks, metals are mostly in group 1, group 2, part of group 3, and then the transition metals. This is why you find the metals in the periodic table. When you look at the left-hand side of the periodic table, which I believe you have there in your textbook, you find out that elements in group 1, group 2, some parts of group 3, this is 1A, 2A, 3A. This is where you find metals. And then you have the transition metals here. So this is the position of elements in the periodic table. So even blindly, when you wake up from sleep and you are asked to locate give an example of any metal, just come to group 1 or group 2 and some group 3 elements. Not all group 3 elements are metal. And then we have the transition metals. So metals, as I have said earlier, apart from this electropositivity, or I may say the electropositivity determines some of their properties. The main physical properties that are common with all metals is ductility, malleability. They are hard. Some of them are hard, very hard. They are good conductors of heat and electricity. Are you with me? And physically, when you look at all metals, some of them, they have this glamorous appearance. They have these shiny looks, though it depends on the metal. Metals like gold, silver, they have this attractive and glossy looks. And some metals like iron, they are still shiny, though you cannot compare them with these valuable metals like gold and silver. So these are the common physical properties of metals. They are malleable, they are ductile, means you can cut them down, you can bend them, you can draw them out into threads. These are the common properties of metals, and they are good conductors of heat and electricity. This is the common physical properties of metals. And when you look at the chemical properties of metals, you will see that because of this property I've just mentioned, what I've just cleaned on the board, that the ability to donate electrons, they form ionic compounds because they normally release electrons to non-metals that are willing to accept the electron that are being released. So in that case, metals are given out, non-metals are receiving. So they form ionic compounds. If you remember your SS1 chemistry, you remember the electrovalent compounds, ionic compounds, and their properties. Example, like reaction of sodium and chlorine to form sodium chloride. You see, sodium gives 1 electron for chlorine. You know, sodium, if you remember, is the electronic configuration of sodium is 281, and this one is 287. So these 1 electrons come here, and then you have this, you have this. Sodium becomes positively charged because it has given a single electron. Chlorine becomes negatively charged because it has gained a single electron. Anytime an atom or an element releases an electron, it will have a positive charge. Anytime an atom or an element gains an electron, it will have a negative charge. The number of charges depends on the number of electrons that are being given out or the number of electrons that are being received. Here, sodium gives 1 electron to chlorine, it becomes positively charged. Chlorine receives single electron, it becomes negatively charged. So this is an ionic compound. Ionic compound. So all metals react with non-metals to form ionic compounds. Are you following? Are you with me? And then another point I would like to tell you is that metals and metals, they don't react, unlike non-metals. You know, some non-metals, they react, many of them. Let me cite an example. When you look at many compounds, organic compounds, even some inorganic compounds, you find out that non-metals, they react with themselves. Example, carbon is non-metal, oxygen is non-metal. Nitrogen is non-metal, oxygen is non-metal. Sulfur is non-metal, oxygen is non-metal. Carbon is non-metal, hydrogen is non-metal. So all these compounds is a combination of non-metals by themselves. So non-metals can react with metals and they can react with themselves. But for metals, it's not possible. They hardly react, unless in some rare cases. Metals and metals, they do not react. They only form an alloy. They only form an alloy. An alloy is not a chemical combination, it's more like a physical mixture. It's more like a physical mixture of metals. Here comes the alloy. Metal and metal form alloy. It's more like a physical, it's a mixture. It's a solid mixture of metals. That's what you call an alloy. Are you following? And you know the difference between a mixture and a compound. A compound, that is a chemical reaction, sharing of electrons, giving out of electrons, donation of electrons, and so on. But a physical mixture, I mean they are lying side by side. The electrons are intact. They don't play with them whether by transfer or by donation or by sharing. So metals, they do not react metal and metal. They only form alloy, which is a solid mixture of metals. Are you with me? Are you following? So this is a brief introduction about metals, their common physical properties, and their common chemical properties. Now we are going to see what are the sources of these metals. We're going to see the natural sources. The natural sources of metals. When you look at the universe where we find ourselves, yes? Okay. When you look at the universe, you know we have billions, like in our galaxy, the Milky Way. We have hundreds of millions of stars in our galaxy. Who will give me an example of a star that we have here in our system? You know, in our solar system, we only have one star. What's the name of that star? The sun. So there are hundreds of billions of them in the universe. So when a star dies, because they die, after billions of years they expire, they burst. And after that explosion, when they are dying, that is when they release these metals, and that's why they came into our solar system, and that's why we have them in different planets, different metals. So the composition and the presence of metals are as a result of explosion of dying stars. It takes them billions of years to die. So scientists have discovered the relative abundance of this metal that we have been mentioning. When you consider the Earth crust, the most abundant element in the Earth crust is aluminium, then followed by iron. Are you with me? Then followed by calcium, then followed by sodium, then potassium, and then magnesium. In the Earth crust, aluminium is the most abundant element in the Earth crust, followed by iron, then calcium, then sodium, then potassium, and then magnesium is the least. So these are the most abundant elements in the Earth crust. There are other elements, but these are the most. So the percentage of these elements is quite high, and this is their order of decreasing order of their composition in the Earth crust. So are you following? Aluminium is the most abundant, while the least is the magnesium. But as I have said earlier, there are other elements: chromium, vanadium, titanium, many others. But their composition is not as high as these 5 or 6 elements. Then compounds of metals. Metals forms oxides, sulfides, halides with non-metals. Metals, can I clean here? Metal forms chloride, the compounds of metals. The metals. And another point you need to know is this. Most of the compounds of metals are oxidation products. Oxidation products. Because if you remember your SS1, or I may call it SS2 chemistry, you remember oxidation. Oxidation is defined as the release or loss of electrons by an atom. Are you following? So oxidation product, because metals, they readily donate electrons away to become positively charged. That's why most of their reactions with non-metals, they are oxidation products, meaning they are compounds formed as a result of oxidation of the metals. The examples are this: the oxides, the sulfides, the halides, and so on. So these are the typical examples of the compounds of metals. And I've said earlier, they are oxidation products, because anytime when we say oxide, we are referring to a combination of a metal with an oxygen. A binary compound of oxygen with a metal is what we call metallic oxides. So you will find out that the metals donate electron to the oxygen, thereby becoming oxidized. The same thing with the sulfide. Is a combination of metal and sulfur. The metal donate electron to the sulfur compounds, and then they become sulfide, and then the metals become positively charged, hence oxidized. The same thing with halides. So most of these compounds of metals, they are oxidation products. Are you following? Okay. And the bond, as I've said earlier, the bond formation between this element and this compound, I said is what? It's ionic bond. It's ionic bond. Because the metals, they have this charge, and then the non-metal, they have the minus charge. And you know different charges attract. When you have plus and minus, positive and negative, there will be a force of attraction. So that's why these ionic compounds, they are held together by electrostatic force of attraction. Electrostatic force of attraction, because of this difference in their charges. Are you following? Are you with me? Okay. Are you with me here? Okay. Then we go to the extraction of metals from their ores. Extraction of metals from their ore. Before then, I would like to tell you something. The reactivity of metals. Their reactivity differs. If you remember the electrochemical series, whereby we have different elements arranged based on their reactivity. Some metals are more reactive than others. Some metals are quite more reactive than others. Elements like potassium, calcium, sodium, magnesium. Let me just stop here. They are on top of the electrochemical series. When you look at their book, when you look at your books, you will see the table is right there. All the common elements are there. As you are going down, the reactivity decreases. So when you go to the element that are at the bottom of the electrochemical series, then the reactivity decreases. For instance, copper, mercury, gold, silver, so when you consider these two examples, check out your book, you will see the electrochemical series. The reactivity decreases. The most reactive is potassium. It goes down like this, up to the level whereby you come to elements that are least reactive, like mercury, silver, gold. So elements that are highly reactive, they are not found free in nature. They are always in a combined state. Elements like this that are highly reactive, they are always found in the earth crust in a combined state. While elements that are less reactive, they are found in free states, sometimes, or usually. That's why gold, when you see gold, it's just gold. When you see silver, it's just silver. But for potassium, calcium, sodium, and magnesium, you can never see it in a free state. It is always in combined state. Are you following? Because of their reactivity. You keep them, they will react with any available element around. While a less reactive element, as I've said, they are found free in nature. So that is where the issue of ore comes. The issue of ore. Let me do it here. Let me clean here. The issue of ore. So because they are highly reactive, I've said earlier, because they are highly reactive, they are not found free in nature. They are always in combined state. So the format, the nature in which they are being found in the earth crust is what we call an ore. So ore can be defined as it's a compound which contains at least one valuable element or metal in it. An ore is a compound or is a material containing at least one valuable element or metal in it. That's what we call an ore. When you look at them carefully, you'll find out that some O's contain more than one element. Some they contain 3 elements, some 2 elements, some a single element. It all depends on the O. So what we are going to discuss now is the extraction of these metals from their ores, the common ways we normally get them. Are you following? So let me give you an example of some metals and their ores. That's how they naturally occur in the earth crust. Like aluminium, it occurs as bauxite. We call it bauxite. We'll talk about it later and maybe tomorrow in the next lecture. Then this is the common ore for iron. It exists as this, which you call hematite. It also exists like this, which is magnetite. We also have a combination like calcium and magnesium. They exist in a compound like this. And we call it dolomite. We have other compound like lead. It exists as a PBS, which is galena, lead. Lead. Potassium also exists as saltpeter, which is KNO3, potassium nitrate. So all these are the natural forms in which they exist. Are you following? So that's what we call, these are the O's. You can't get aluminum just like that, or potassium, or calcium, or lead. They normally exist in this form. When you look at your book, you will see other O's for tin, for sodium. Sodium normally exists as a rock salt, sodium chloride that you know, but it contains some impurities. So the common techniques. So are you familiar with the concept of ore? All these are ores of this element. Because they are highly reactive, they don't occur in a free state naturally. They are always in combined form. So this form where they exist in nature is what we call an ore. Are you following? Okay. Can I clean here? Can I move forward? Okay, I should give you a chance to write. When you look at your books, you will see them. There are many elements like this because of the size of the board. I cannot. But you check out your textbook, you will see a lot of O's of all the metals and how they commonly appear. And the common techniques we normally use in their separation are 3. That's what we call pyrometallurgy, whereby we use high temperature. We apply heat. We apply heat to separate the metals we are looking for. Then we have the hydrometallurgy, whereby we normally use water, jet of water under high pressure. We apply water to. That's what we talk about flotation and other techniques, which we'll talk about when we start talking about the extraction of some metals from their ores. Then the third one is electrometallurgy, whereby we use electrolysis. We apply electricity to the ions because they conduct electricity and they become separated because of the electrolytic process. We'll talk about it maybe tomorrow in the next lecture. Are you following? Can I go ahead? And one of the most common is electrolysis. One of the most common techniques is electrolysis. And when we say electrolysis, what do we mean? Electro means what? Electricity. Lysis inside, when we say lysis, means breakdown of something or breaking down of substance. So application of electricity to some compounds in their molten state or in their liquid state is what we call electrolysis. And it's one of the most applicable techniques that we normally use in extraction of metals from their ores. If you remember, electrolysis is always like this. Let me clean the board clearer so that you guys can see. Let's say you have a large container like this. You have your electrolyte. So we normally use our electrodes here, dip them into this mixture. This is negative, this is positive. We call this one cathode, and we call this one anode. So if you have an ion here, whether in a solution or in a molten form, and then you apply electricity to pass. Sorry. You have your voltage here. Let's say you have this, for instance, you have, let's say, magnesium chloride. Immediately, you apply electricity, the compound will split into its ions. Magnesium will become this, and chlorine will become this chloride ion. Magnesium, being positively charged, will be attracted to the negative electrode. So magnesium will move here and become deposited. It will come here, it will release an electrons, and it will become deposited at the cathode. While the chloride ion will move here, because they have minus charges, so they will be attracted by the positive electrode. So they will come here, they will gain electrons and become deposited there. So this is the common technique we normally apply in the separation of metals. So your magnesium will be here, being separated from the chlorine. Are you following? So electrolysis is one of the most common techniques we normally apply in the separation or in the extraction of metals from their ores. Another example is the reduction of the oxides. Reduction, you know, reduction is the opposite of oxidation. Oxidation means maybe addition of oxygen to your compound or loss of an electron by a compound. So in this case we are talking about oxygen. When we say reduction, it means removal of oxygen from compounds. Because as I have said earlier, some of these O's, they exist at their oxides. So reduction of these oxides will give you the pure metal. Are you following? Using strong reducing agents. Example. So you can see electrolysis is number one. Electrolysis, number one, is a common technique for their separation. Two, reduction of their oxides. Reduction of their oxides. Example, you have carbon monoxide and this. Are you following? You have carbon monoxide here, or carbon 2 oxide. It's a reducing agent here. It is reducing the iron 3 oxide into pure iron. Are you following? Are you with me? You are using the carbon monoxide as a reducing agent to completely reduce the iron 2 oxide into pure iron. And when you want to balance it, I think it is like this. So you have your pure iron here. So apart from electrolysis, whereby you use electricity and you get your metals, another technique is the reduction of their oxides. Example, this is iron 2 oxide, iron 3 oxide. Carbon monoxide is a reducing agent. You react them together, it will give you carbon 4 oxide, and the metal will be reduced to pure iron. Are you with me? Another example is the reduction of their chlorides. Reduction of their chlorides. Their chlorides. Typical example, when you have titanium chloride, you're reacting with sodium and you are looking for titanium here, it will be reduced to this to give you sodium chloride plus titanium. You have 4 here, and then you have 4 here. This is another example of production of, or extraction or separation of metals from their ores. reduction of oxides, reduction of their chlorides, because this is titanium chloride. It has been reduced by sodium metal to give sodium chloride and the pure titanium. The last is the reduction of their sulfides, which I am supposed to, let me squeeze and write it here. This is the reduction of their sulfides. When you look at this compound, you find out that no oxidation of this is sulfide is being reduced. Copper 2 sulfide, or copper 1 sulfide, sorry, reacting with oxygen to give you sulfur 4 oxide and the pure copper. In chemistry, we normally call this kind of reaction roasting. We call it roasting, just like roasted meat or roasted fish. We call it roasting, R-O-A-S-T, roasting. So this kind of reaction is called roasting. It's another way whereby we generate pure metal from ores. So you can see all these three reactions are reductions. Reduction of sulfides, reduction of oxides, reduction of chlorides. In each case, it will give you the pure metal, the pure metal you are looking for. Are you following? So now briefly we will start introducing the alkali metals. Now we have seen the general properties of metals, their nature, their relative abundance, how they exist in their ores, how they are being separated or extracted from their ores. At least you have an idea now about it. Are you following? Are you with me? So now we are going to see some classes of metal, classification of metals. Classification of metals. We just see example of these classes of metals, their properties, their uses, and so on. Alkali metals. Alkali metals. These are group 1 elements of metals. These are group 1 elements of metals. They are like this. This is number 1. Then we have sodium. Then we have potassium. Then we have rubidium. Then we have cesium. And then we have francium. These are the group 1 metals or alkali metals, group 1A metals or alkali metals. Are you following? But this, especially this one, this and this, but in particular interested this one is highly radioactive. In fact, it doesn't have a stable isotope. It is highly radioactive. So in chemistry, we hardly play around with it when we are dealing with the properties of group 1 elements. Francium, this is lithium, sodium, potassium, rubidium, cesium, and francium. So francium is highly radioactive. In fact, it has no stable isotope. So let me briefly take this. This is the most typical member among them, sodium. I will briefly talk about it and then see what we can have before the time runs out. It is highly reactive and it is produced by electrolysis using a down cell. The electrolytic cell that is normally used is down cell. Sodium hydroxide interact with when you have sodium chloride as a typical example. The electrolysis I have just mentioned above. When you have an aqueous solution of sodium chloride or molten state, the sodium will split and move to the cathode and become deposited there. So the special cell, the special electrolytic cell we normally use in the production of sodium is called down cell. Are you following? For sodium, electrolysis of the salt, sodium chloride, sodium will go to the cathode and become deposited. I don't think I should write it again because I have just mentioned about the concept of electrolysis in the separation of metals. Sodium will move to the cathode, it will gain electrons and become deposited. Are you following? Should I write? I don't think I should write about that electrolytic cell. It's simple, just what I have cleaned earlier. And another peculiar nature of sodium is this. Sodium reacts with water to form an alkali and hydrogen gas. This is one I think I can clean here. Sodium reacts with water to give you a base plus hydrogen gas. React with water, but the reaction is kind of a dangerous reaction. You know, this is a base, we call it sodium hydroxide. If you remember our common alkali, our common base that we normally have, it reacts with water to give this base, which is an alkali. It's a very important compound, which is in high concentration is very dangerous, it's corrosive. And then it produces hydrogen gas. And you know, anywhere you have hydrogen and there is oxygen available, there will be reaction. Hydrogen reacts with oxygen explosively to give water. That is when you are talking about this reaction. The reaction is quite explosive. That's why anytime you have a pure sodium sample, sodium metal, if you have a sodium metal, when you put it in water, it reacts explosively. This is what actually happens. Reaction to give you this, to give you hydrogen, and the hydrogen reacts explosively with the free oxygen in water to give water. Are you with me? So that's why I don't know whether you have seen an experiment whereby we put sodium metal in water. At distance, it looks interesting. You'll be seeing that as if the sodium metal is an what do you call it? Like at distance, it is also used in the reduction of titanium chloride, of titanium from titanium chloride. Like the example I gave earlier, the reduction of chlorides. It is also used in the production of anti-knocking agent. You know, initially we normally use a compound called tetraethyl lead. Anti-knocking agent. Sorry. Anti-knocking agent. We normally use it in petrol engines. Anti-knocking agent. So initially we use tetraethyl lead. So initially we use a sodium lead alloy in conjunction with ethyl chloride to give you tetraethyl lead. But though it is no more in use nowadays, but before we normally use tetraethyl lead as anti-knocking agent in petrol engines. So sodium plays a vital role in the production of the TAL, and it has many uses. Like sodium hydroxide, it is used as in the cleaning of pipes, cleaning of drainages in higher societies. Sodium hydroxide. It is also used in the production of many important compounds, many salts. Remember sodium chloride, the table salt you normally use is sodium chloride. So the importance or the uses of sodium, they are innumerable. There are many. And the common example of sodium compounds are sodium bicarbonate, which is used as a baking soda. Common example of sodium salts, or sodium compounds, sorry. The baking sodium bicarbonate. Take sodium. Example of their compounds. Sodium bicarbonate. Sodium hydroxide. Sodium carbonate. Sodium chloride. Come again? Are you talking? Any question? And then sodium silicate. We also have sodium silicate. So this is sodium bicarbonate. The baking powder you normally use in the production of bakeries, cheese. No, not really cheese. When you are producing cakes and other snacks, sometimes you use a baking powder. The main component is sodium bicarbonate. Then we have the sodium hydroxide I've just mentioned. It's a base. It has wide application in many industries, chemical industries and drug industries. Then we have the sodium carbonate. It has also wide applications. Sodium chloride, no one to tell you about the uses. Sodium silicate also, it has various uses in different industries, especially pharmaceutical industries. So are you following? Are you with me? I don't think I should define this for you. This is sodium what? Sodium bicarbonate or sodium hydrogen trioxocarbonate 4, the IUPAC name. We call it sodium bicarbonate or sodium hydrogen trioxocarbonate 4. Sodium hydroxide, this is sodium carbonate or disodium carbonate or sodium trioxocarbonate 4 as well. Are you getting me? This is sodium chloride, this is sodium silicate or disodium trioxosilicate 4. So these are their chemical formulae and their common names. So these are the common, there are many compounds. There are more than hundreds of compounds of sodium. They are innumerable, but these are the common ones that at our level here we'll be dealing with. So any question before we go to I think I will come to a halt and then ask questions, if any. Or maybe you may ask questions before we round up for the lesson, because we are coming to the end of the session for the day. So any question before I start asking my questions? Because I may likely ask you a question. If you don't have them, we can. Shall I ask a question? Okay, I'll give you homework maybe tomorrow when we come. So I am really thankful for your patience and everything. So tomorrow we'll continue with the alkaline earth method. That's the end of this session. Thank you very much.